Hello and welcome back. So we are going through programming quantum computers and we're up to chapter 9, doing actual application stuff. So this should be interesting. So Matt is going to be leading our discussion today. And take it away, Matt.
Yeah, so leading is a loose term. I can walk us through this chapter was kind of interesting, just not a whole lot of code, just more conceptual items. But yeah, if you wanted to go ahead and bring up your book. And I will. And I like the physical book because it allows me to write notes, flip through it, and read it in different places out in my backyard or something. But I'm finding the need to buy it twice. But anyway, so yeah, here we got into two interesting concepts, and I think it's things that we've talked about in other chapters, and he alluded to in the last chapter. But yeah, he basically says, okay, we've had all these nice, very simplistic examples where we're seeding data with these nice little operations to get it the way we want. But of course, in a computer program, you need to be able to take in data. You need to be able to take in data that's of any real form. And so he said, okay, so in this chapter, we're looking at two questions. And he says, how do we represent complicated data types in a QPU? And so yeah, he mentions, we can talk about integers, and he mentions positive. We did a little bit of negative integers too. What do we do with irrational compound types of data as vectors, matrices? And of course, I'm also thinking, well, beyond that, do we use anything sort of like objects? Do we have a concept of objects in QPUs? Things like that. And then beyond that, okay, how do we read it into the register? So first of all, we have to know how to implement it. And then second of all, assuming we have this data somewhere, how do we read it into it? And he does say, we've been initializing by hands using write operations. If we're ever going to use large amounts of data, obviously that's prohibitive. It does not scale well, of course. It's non-trivial. And so something that, our conventional ideas of what RAM is and how we normally grab data won't work out. So we're going to, he gets us into how to store data first. And feel free, both of you, to jump in with ideas or comments if I skip something or as you have ideas. He talks about vector data, and I will tell you right now, I want to go back and refresh some of the basics of vectors. The last time I actually calculated anything to do with a vector was like 20 years ago. And I think it was either math courses or I did have a little fun with it, learning how rendering engines worked when I was in a graphics programming class. That is the extent of it. So some of the concepts he talks here about, I easily had no clue what he was mentioning. So if either of you have some insight, because I started going down the rabbit hole of Google and got quickly lost. So I thought, I need to take another week or something and take a nice, basic vectors course. But moving on, yeah.
One of the things I would say is I use Khan Academy to refresh mathematical concepts. I learned them late in life, so I'm closer to them. But if I don't use them constantly, they're not in the front of my thinking. And so it's just a brief way. So the two big resources I use are Khan Academy and Wolfram Alpha Pro. I pay for Wolfram Alpha Pro because it shows in mathematical calculation. You can you have to pay for that part to show the work so that you can see how vector calculations are done, for example. So those are, to me, they're sort of just-in-time math, if there is such a thing. And so it's a technique I've used because this will be applicable to, in my case, machine learning. And I just, again, if I don't use these mathematical concepts often, then I have to quickly refresh them. And so those two methods have worked well for me.
Perfect, thanks. And I need to do that. And I didn't get a chance to this week. So he kind of starts talking about non-integer data. So we're talking, decimal type numbers. He talks about two common methods coming up here, fixed point and floating point. And he talks about the pros and cons. Again, we're really getting back into the classic idea of how do you represent this thing inside of a computer. And if you remember, we talked about how to represent negative numbers before and simple operations to handle those. So he gets into fixed point, and this was really interesting because you decide how many bits you want to, or qubits to represent the fractional side of things, and then how many qubits you want to represent the non-fractional, the whole number side of things. And this is, I think, immediately attractive to me only because you really can define exactly how accurate you want to get. So if you need to have a number that can handle 1 million in your whole number side, you just make sure you have enough bits for that, and then the fractional side too. What is interesting though is I think it's on the next page. You showed it. Yeah, he comes up with this number. He shows an example, 3.640625, and he does have enough qubits to actually represent that exactly. This, of course, is assuming you know how accurate you want to be, and he picked a number that very nicely fits that. But if I would say if we had 3.640626, 100 millionth or whatever that is, 100,000th place off, I don't know how many fractions we would need. And that again gets to my OCD side. Well, what if I want to represent that exact number? Well, then maybe floating point would be better for you. And so that's where you quickly dive into the edges of finite computers and stuff. Well, depending on what that number is, you got to watch out depending on what you want to do, and how accurate you want to be. And he really only talks about this type of representation, the fixed. He doesn't get into the floating point, at least not in this chapter. So maybe later on he will do that. He even warns you, take care of operations using 2's complement, which is how we added, negative numbers and represented them before. And fixed point encodings can often be subject to overflow. There's the big bad word we all hate as programmers, where the result calculation is too large to be represented in a register. So obviously that's really bad, and this creates, in my mind, a sense of waste. You got to make sure your registers are large enough that you'll avoid any chance of an overflow. And so on one hand, you can think of that, well, shoot, I've got to make this so large, but I'm not reasonably going to use all those bits. But you might, or someone else might. Someone definitely going to use your program in a way you didn't intend. And so that's something we have to account for. So, yeah.
So again, trade-off is, particularly in machine learning, you may say, what is a good enough precision so that I don't overflow? Because as we'll see in subsequent chapters, there's different kinds of examples. There's classical problems, and then there's machine learning problems. And so again, it's sort of implied here, but it does come that it's a trade-off between precision and amount of qubits. And it reminds me, I'm not quite this old, of what I heard. I remember this from database stuff, like when people couldn't store, to a certain value, and that was more of a storage than a computation. Like when way back in the early days of database, they would only store really small, precision numbers because they didn't have the physical space. So it's kind of like, reminds me of that same paradigm where, resources are not infinite or so much that we don't have to think about it, which is kind of what we get in classical computing now, mostly. We don't really have to think about it. So in some ways, I'm like kind of turning the dial back going, okay, we have to think about this consideration. That's how I kind of read this section.
Yeah, I would agree. And definitely in those old days, we learned how to work around it too. You had to put some expectations in place. But if you were dealing with really small numbers, well, maybe you could store that in a field or a value, but you knew, oh, I need to multiply this by 10 to the negative 8 or whatever. So it helped you if you knew you were storing really small numbers, but you weren't storing really large numbers at the same time. You could represent it in a way that you did have the nice accuracy. But with that and like this, and he says later on, of course, you know, if you are representing something as 2's complement or fixed point, just make sure you know that as you're moving data in and out, because you can't change the way you're storing things, and otherwise you're going to end up with a lot of unusable information. So now that we have an idea of how to store this, and he only talked about fixed point again, I'm curious to see how they do floating point later on. He talks about, okay, so how do we import this? And he talks about RAM, which a lot of us are used to. And you're importing data from somewhere into some sort of memory registers that you can act on. And so he talks about how typically the way computers work is you would have an address location, and we'll move to the next slide. So on the bottom left here, he's reading out an address, and then in the RAM, you have on the left side, you get the address that it's stored in. On the right side, you've got the actual values. So you feed in an address, the RAM goes and does, or actually, I think it's before we get to the RAM. It's probably in the hard drive or something, but we go look up the value and then it returns it for you. I guess in this case, the RAM is actually already in memory, which you're looking for, and you're just reading it out to your program you're using. One thing I will state is his numbers didn't line up, and I'm like, this doesn't make sense, because I'm seeing he's reading out of 10, which I don't know if the high bit's supposed to be on top or the bottom. So we got 10, and then you're reading out 100. Well, if he's got the high bit up here and the lower bit towards the bottom, why does he have the high bit on the bottom and the lower bits on top? And if you actually go to the errata, you'll find out that they actually did correct this feature. So instead of 10, it's actually 01. So he's got the lowest order bit on the top, the highest one on the bottom. So it's actually 001 and 01. So it does line up. But I think I spent a good minute or two just rereading the paragraphs going, I don't understand your picture. So I'm glad I wasn't fully crazy. And so I saw that. So he, talks about it, you know, I just want to initialize it. RAM works perfectly fine for conventional values and just using write or read operations. And he does say this is precisely what we've been doing. He's got a very simplistic example with 9.1. So I'll go ahead and share my screen as we go over the code. Let's see. Okay, and then can you see Mike?
Yes.
So he's got Q1. He has a vector, he calls it, or an array right here. And we've got the values, of course, 4, 3, 5, 1. And so he initializes his qubits. He talks about the RAM before. Then he actually does this increment operation where what he's doing is he passes in the array and then the index we're going to use, and then the register that he can utilize as he's operating on it. And so even though he's got this array here, he's literally just saying, okay, well, give me the value that's in the array. There's not a whole lot of magic going on here. And if we run it, and I've already got ran here, you can see down below, he said, let me clear this. Well, okay. It was 4351, and then he incremented the value that was an index of 2. So, and you can see actually he did load the initial value, which is 5, and that is in our index 2 over here. He does his normal increment operation we've all seen, and then he just reads it out. And of course, now it's a 6. So that's, again, not mind blowing, but I think he's just saying, okay, you can read in and out, no big deal. And then also, if you're interested, here's his updated graph on their errata page. I love how they have their errata in a GitHub site. I think that's the coolest thing. So good, props to them for doing that. But Jeremy, if you want to go back and share your screen.
Sure.
Sorry, we're going to be doing that back and forth a bit here. So there's that. And then, so he talks about how he's using conventional CPU and other things we're doing. Let's see, I was trying to remember. So we talked about, yeah, this fails. How do we represent superposition? How do we get that in and out and do things like that? So, and he's talking about, this is where we actually get into QRAM. QRAM, the point of it is you're able to have represent super items in superposition. Where I kind of fell apart here though is, and definitely I'd love to hear your thoughts. I thought he was saying we can actually store the state of superposition somehow in our data, in our RAM or something. And I don't know that he actually is. I think he's still storing classical values. What he's using superposition for is to say, well, we may actually pull multiple of those values. So in this case, he's setting his low bit to 1 and his high bit, he's put a hat on it. So we're either going to grab, and I'm assuming his graph is correct, we're either going to grab 110 or 111. We don't know. And then he's going to increment that. And so, yeah, I don't know what your thoughts were. I thought his idea of QRAM was, well, how do we store the state of superposition in RAM? How? But I don't know. Maybe that's doesn't even make sense, since you can't read something and retain superposition. So how would you read something into a data field?
Well, so for this particular example, this example 9.9-2, it does not use superposition for what's in QRAM, but I think based on the 9.3 example, where it's showing how we can, rather than, the next example actually shows a separate qubit for each of the values. And the 9-3 shows how to use superposition to store all of the values in a much smaller number of qubits. And so I'm kind of getting the idea that the 9-3 is actually the precursor to having your QRAM with superposition data in it. So that's kind of the impression that I got.
Okay. Yeah, because this one, and if we go over the code, let's see what else is, oh yeah, and then we get back in the register, sorry. If we take a look at this one, do this. I will get faster with this. So we got 9-2 here, and this started to look real complex really fast. But as I broke this down, and I did want to rewrite it, I just didn't have a chance to get into it. Where he starts is he's actually, again, I had to really kind of figure out what he was doing. We have our same vector or our array 4, 3, 5, 1, and he's actually encoded that here. So his QRAM 0 is our representation of 4. And so we can say we've got 4 in there. He's writing that. We've got 3 in our second area. We've got 5 in our third, and 1 in our fourth. So that's exactly what these are. Mm-hmm. And then later on, we have our QReg up here, which is where he's doing the work. And then we have our address. And so if we go back to our diagram here, the address is where we're saying, this is where I want you to get the data from, and bring that back to me. So in this case, he's actually, like we said before, he's got a 1 on the high bit and he has the bottom, the lowest bit. So we could be grabbing it from either 1 or 3. We're not sure. This is one of those things. This is all under that QRAM load. And if you really want to, you can kind of see what he's doing there. He's got some interesting things, but basically he's doing a lot of swaps. And I think what he's doing is saying, I'm going to load the information that I need from one of these 4 registers into my QReg, where I'm doing my work based off of whatever I'm reading out of the address space.
Yeah, and I kind of stared at this for a very long time to try to figure out what it's doing. And what I got from the separate function QRAM swap to 0 is, if you kind of look at, the big section with all the swaps in it, kind of the first three are saying, well, depending on the state of address 0x1, I'm going to swap QRAM 0 and QRAM 1. So maybe I'll swap those two, and it's all, all 3 qubits from each of those registers. So if you kind of look at it, it potentially swaps all of the values with each other until it gets the one that I'm looking for into QRAM 0. And so once the value I'm looking for is in QRAM 0, then those last 3 swaps put it from QRAM 0 into the QReg, where you can operate on it. And then doing it backwards, or actually doing the same thing again in the store section, puts everything back in the right order.
Yeah.
Again, based on the addresses.
And he loads it, like you're saying, it determines which address we're looking for. It does the increment that we've all seen in that working register, and then it loads it back, but it doesn't actually do it quite backwards, which is interesting. You can see it's got the same swap operations. And I have a feeling that's because it's not deleting or writing over data. It's just swapping individual lines. So whether it did this one first and then something else or not, I don't think it actually changes the outcome in the way he does it. But we're not seeing it actually literally done backwards like we're used to other operations. But I added these read statements over here. And so when you run it, and I'm not fancy enough, maybe you guys know how, to actually print out what I'm reading. So at least not off the top of my head.
Can I show? Because I actually did do that.
Yeah, you do it.
Okay.
I did this and ran it several times to see what address are you reading and did it actually increment that particular location in the array. So definitely take it away.
Okay, so I'm assuming you can see my screen. Okay, move this again. So what I did was I added some reads before and after. So to read it out, I created, oh, jeepers. Let me run that again. So this shows the before and then the after, and then which address was incremented. So because we're adding the address 0, or the 0 bit of the address, then the value could either be 2 or 3 based on the superposition of that. And so what I did was I added some reads so it would read out all of the, both the address as well as all of the bits. And then I did it separately so that you can see everything in little chunks. But basically, if I run this multiple times, come on, you'll see that
it's down below.
Yeah, I don't know if you can see the numbers changing for the address here, and then these 2 values will actually change depending on how it's feeling with that had. And so then the same is true down here. This says, okay, well, I'm using address 2, which is the 3rd item. So the 5 changes to a 6. But if I run this a couple times, now it's using address 3, which is the 4th value. So it changes the 1 to the 2. So that's what I did with the reads.
Yeah.
Just so I could look at what was coming out again. And obviously that destroys all my data. But
yeah, so yeah, I was under the impression we were going to somehow store some sort of superposition data in our QRAM, but this was a slightly different example.
So the way I took this example was, it's an example, like Jeremy was saying, to show you what you might think to do. And then the next example will show what is preferred because it uses less qubits. And that's the way I took it. It's, again, it's an interesting pattern. When you do the reads, I think in my head, console write line in JavaScript, which is not the same thing, but, or debugging, so this is a technique that we have come to use as we've been learning to store the data and read it because, we just need to see it so we can understand what's going on. which to me, if I think about this, if I were going to use this in production, I'd be like, okay, it's going to take a longer time to develop anything because you don't have this ability to see in easily. We've seen some other ways you can see in without destroying with the other tools. We had the QFTs and all that kind of stuff, but we tend to go for the quick and dirty. And I just wonder as we continue learning how to be quantum programmers, if that's a technique that people actually use, or if that just comes from our classical background. I'm just curious, right? Because that is the tendency, like log it out, right?
Yeah.
And so, maybe I'll take that as a research and I can just actually look and see, because I'm just curious, like, is this a good instinct? Like, is this right? Is this what people actually do? Or is there a better way to do this, to examine? Because I think we're all feeling like it's not right, but it's what we have, right?
Yeah, no way I would have, because I've been having that same thought too. And like, oh, you're going through the debugger and like, okay, I'm in loop 35 and let me throw my areas. But I'm thinking, okay, well, I think in this, you have to come up with a formula or a set of operations that does a goal. And can you verify that operation is correct? Maybe I don't need, when I stick it into my program and I've got 8 different operations, I don't need to debug in there as long as I know that one particular operation does what it says. And it makes me go back to, okay, someday we're going to have libraries of operations and you yourself won't be debugging in that library. You'll just know this is the operation and I trust that it does what it says it does. But as a library builder.
Right. Well, but then that goes to the greater question of how would you test this?
Well, yeah. So now I'm in the test-driven development, right? So I'm thinking, okay, I have an operation, I have inputs, and I'm going to test this set of outputs, right? But you can't test once or twice. So what does our test library or setup look like? Am I going to run 1,000 iterations?
Yeah. That's what that's what I've actually seen. Again, more machine learning like, where you just run 1,000 iterations and you look at the percentage within the range, which again is very new for classical programmers. And that's my intuition that that's what you would do here. But it just still feels weird, even though I've been doing machine learning for a while, that you can accept that level of imprecision, if you will.
Yeah, it's exciting, I think. I don't know, part of me gets excited about that. Because
that's a good attitude to have.
Well, machine learning and data science, my experience is about this big, but I work for a school district and it's always been the idea of, can we harvest that data and identify students who would do well in certain classes, maybe even with certain teachers. You've got a student, let's say, who is habitually a poor student as far as grades, but they just are stellar in this other area. And you realize this teacher is great with students who don't learn using the traditional model. So could we somehow use machine learning to identify that? And so I'm thinking, okay, well, you develop your model, but your model is not 100% accurate all the time. You're gonna find kids or data points that are outside your model. Well, yeah.
Well, and one of the ways that you combat that is with more data, and using quantum methodologies has the promise to allow you to do that because of the speed up. Because of course, with machine learning, the hindrance is the amount of time it takes to train the models when you have huge amounts of data. So it's all probabilistic. So it's just very different than classical. And me coming from genomics, I'm really getting a window into this. What percentage of the genome do you look at? And there's been this whole movement towards what they call junk DNA, because human DNA, for example, is 99% the same, and it was considered, the other, what seems to be the same has no relevance. What they were actually finding that it does, because it's in the chain of making your proteins in your body and all that. So, but how do you analyze that? Because you outrun out of resources. So that's where quantum comes in. It's actually one of the reasons I'm here, because want to be able to start to learn these techniques. And of course, just foreshadowing, the last chapter of the book is QML, which is quantum machine learning. So, but we're getting ahead. So
very exciting. Okay, so Jeremy, if you want to throw your book up there.
Yeah.
Fortunately, there's not a lot of code examples, so we won't be jumping thing. So now we get into vector encoding. And again, this is where I'm going to really rely on you two to interject comments as we will. I'm used to vectors again when, graphics rendering and things like that, and they're completely in coordinate systems. I'm used to either 3 variable vectors or 3 by 3, 9 matrix. I'm not used to. I don't know why we have 4 numbers in a vector. Other than that, that's what he wanted to represent. And he talks about machine learning. So maybe 4 unit vectors are very normal machine learning, and you can definitely talk about that if so. But I like how he says, again, like, oh, well, this is the way you're used to doing it. This is the way actually we could do it. And he says, oh, this would actually be very easy to represent in 4 different sets of registers. And you're right. Oh, that's easy. And that would probably be our first assumption. Oh, that's no problem. I like how he instantly says this is pretty naive, and that's good. That's why I'm reading a book. QQs are our scarcest resource. So definitely, yeah, this is really wasteful. And right here, obviously, majority of the circles aren't even used. I like how he also said it doesn't actually require any QRAM. We're not getting our benefits. And then later on, he talks about to exploit the QPU's power, we actually want to be in the business of manipulating phases, superpositions, and something that's hard to do if we're treating it like this. And it's like, oh yeah, well, let's do it in a way that actually exploits the whole reason why we're here. Cool QPUs. So it talks about how we can store this in a single QPU. And so I'll go over the next one. And this, is because the notation that we've come to know and love. And so intuitively, this actually sort of makes sense as we see, this is amplitude 1, 0, of course, is blank. 3 has the highest magnitude. And so here, instead of using 4 separate registers, we're only using 1. And obviously with things in superposition, and later on, I'm assuming we'll play with angles, this is much more, ready for us to do all the fun magic that we've been learning. And so he does talk about how do we represent that. Of course, our circles, at least in this notation or in the spherical diagram, we can go to 0 to 100% filled. There's no such thing as a 3. And so he talks about normalizing that in such a way that you can actually represent the magnitude of how much the circles are filled based on their numbers. And again, I don't know if this matters for me right now in my limited understanding. You two may have more to say. I think I'm skipping a page with my comments. So he talks about, let's see, was it here? He talks about the gotcha where, yeah, right over here, where the amount of the circles filled in the magnitude is actually based off the square. So, because in my head, okay, if all the circles should add up to 100%, how do you have a 80%, a 53%, a 27%, 0? And this is because we're squaring. And so he definitely says, watch out for that when estimating your values, making sure that, don't forget you're talking about the square of this. And so these last few is really him talking about how we get those types of numbers in there. Now he's got an 8 unit vector here. And he's using vectors that are power of 2 because we're using qubits, we're using powers of 2. So I suppose we could have a 5 quantity vector. We would just have a 4-bit register with 8 circles, and 3 of them would just simply be unused. I'm assuming if we had to do something like that.
I'm not sure if that's true or not. And I haven't thought about this, just because for the example 9-3, I kind of did the step through and watched all the circles kind of move back and forth.
Mm-hmm.
I don't know if there's some that aren't filled in, if it still works the same way or not. I mean, I guess logically it seems like it would, but with quantum, I don't count anything out.
Well, as we're talking, I just opened 9.3, and we can talk about it later, but I removed one of those.
Oh, you removed one of the values?
Oh, he's talking about 9.3. So let's go ahead and bring it up. And then this is our last code. So we won't have to swap back and forth like this anymore. And so here's his 9.3 example. And he does, I think the whole thing is he is telling us how he can encode this vector into our various amplitudes here. I can't remember if he's actually operating on it. I don't think he is here.
No, I think this is just encoding it.
Mhm.
Yeah.
If you scroll to the right, you'll see that on the register. See, it's just encoding.
Oh, yeah. Yeah, he's not actually doing the operation. So that's quite a lot to encode this. And of course, I'm sure that gets a little more hairy as we do other things. And he talks about other strategies. But I did try. I removed the last item here in his array, and I instantly got an invalid array length when I tried to run it. I don't know if that is an error inherent to the program, or if he actually has error checking here. I didn't see any right off the bat.
That might be, so there is that oh, okay. I don't know. Line 6 is where he's using the vector length. And I don't know if, no, see, anyway, I don't know what I'm talking about.
Well, he does call out length, so he's not hard coding it somewhere.
Yeah.
But yeah, when we're dealing, and I can't put a 0 because that's real data, right?
Yeah,
0,
I actually added 6 more values to it, and I got an extra qubit in the register. So.
Oh, and did it actually run?
Yeah, it did.
Okay.
Yeah,
So,
I just mirrored it. I did 3 6s and then 2 5s and 2 1s and a -1, just to see how it would come out. And
so we have 8 now. You added 6, so that would have been 14.
oh no, I'm sorry. I added all 8 of them
Oh.
just in reverse order.
I'm not going to reverse it.
Yeah, that's fine.
But you did this.
Yeah, so it's still
Yeah.
divisible. And then if you make your circles bigger, it still follows the same type of pattern
Yeah.
as
Oh,
far as the,
that's nice.
wow.
I should have used. Yeah, that's good. So yeah, it actually does. That's interesting. But if I were to cut off only some of these, I'm assuming we'd have to have some sort of combination. So yeah, it says invalid array length. I do like
Yes.
how adding his number of qubits based off the math log 2 of the length. So that's
Well-
how it.
Well, it says the comments in line 10 and 11,
Mhm.
we've ensured our input vector has a length that is a power of 2. So I think that is, and then implemented in line 15. So you have to have the lengths that are powers of 2.
Yeah.
I think that's where that comes.
And again, this is my limited knowledge of vectors also. So I don't know if we had to represent a vector that wasn't a power of 2, if we would have to do that some other way.
Well, is there such a thing as a different log function we could use? It's squared, so is this, I'm kind of at the end of my knowledge of this too. Like, is the log 2 the fact that it's squared, or
He's doing a log 2 because what that does is it gives him the number of bits he needs. So yeah, if we had 8 units to encode, he says, oh, I only need 3 bits to have up to 8 units worth of information.
Yeah, that wouldn't generate an invalid array length, though. There has to be something in the amplitude encode function that maybe it's running off the end of an array or something.
Yeah, I'll have to go through that. I'll play with it over the week and maybe we can talk about it next week. But I mean, this is kind of a simplistic example, and it's to more of the crux of what we're trying to get to.
yeah, that's what I got, that he just was like, okay, encode it in a quantum fashion. I'm just going to make it that it has to be, like it said, the vector length is a power 2, just to simplify the problem.
So go ahead and share your screen, Jeremy, and that's the last time we'll have to swap back and forth. And so he talks about some limitations, generally unreadable. That's our issue. Not a big deal for inputting data. Obviously, how do we get it out? And so we've got some limitations. Of course, we can still extract useful information like we've learned in the past with some ways of encoding that in our phases and things like that. He also talks about his requirement for normalized vectors. So we talked about that a little bit. How do you get your vectors of some sort of form like this into something that you can represent? And my only thought with that was, okay, that adds extra computing power. You have to have a few operations. And assuming at the end of this, if you want a non-normalized vector back so you can act on it, you would just have to do that in reverse.
And those are all classical operations, so they could theoretically be done outside the QPU.
Yeah, that's true. Yeah, definitely. So this matrix encoding, my limited knowledge of matrix, this was kind of interesting because I liked where he was going with us for this. One thing he talks about is, okay, so if we have matrix, and I'm going to again relate my graphics and rendering knowledge here, I would use 3x3 matrices all the time. You're multiplying things against each other as you're finding out which direction light is going, or you're rotating, or you're making something larger or smaller. And so he was saying, yeah, we might have a matrix. And it's interesting. He said, well, we could encode that again in our registers. And so if we had a 4x4 matrix, you could have 4 registers of 2 qubits each. So we'd have our 4x4. And he said that's one way of doing it. One thing he talks about, though, is we often are multiplying matrices against each other. And so he says, well, let's see, it makes sense to think about encoding matrices as QPU operations. And so my thought is, okay, let's say I had an input matrix. I would encode that somehow, but then I wanted to multiply it against something. So again, in my rendering terminology, I would scale that or rotate it. I'm going to multiply it by a particular matrix. Multiplying is really just a set of operations. So I thought, well, that's neat. I'm not actually encoding 2 matrices and then doing operations in between them. I would actually encode 1 matrix. And then the operation I want to perform is a set of operations that I've built out, not a second matrix. And so he talks about, well, there's our own pros and cons, but how do we do this? How can a QPU operation represent a matrix? And what he kind of does, and we're pulling on eigenvectors and other things, eigenphases that we learned in the last chapter, and I didn't quite have that 100% down. So I think I got the concept of what he's doing here, even if I certainly couldn't do it myself. But again, going back to like test-driven development stuff, if we can say, well, here's a matrix, and if we encode that in a certain way, we have these cool eigenphases, and we know that operations are uniquely identified by their eigenphases or their angles. So if we could come up with some operations that decompose into those exact type of angles that represents what our initial matrix was, then we know that we have a set of operations that actually represents that matrix. That wasn't a very articulate way of saying it, but does that kind of make sense to you two? Mm-hmm. I thought that was kind of unique use of some of the cool tools we had from last chapter. So if I had to multiply a matrix by something, I would find out what those very specific operations are, and I would use those operations in my circuits. And again, me being OCD, I like the idea that we can come up with operations that I know for a fact represent what I'm trying to do, because we're relying on those eigenphases and things like that. He goes into start talking about ways to do this. And again, this is where I'm going to get real fuzzy. So if you have heard of Hermitian matrices and how they act, definitely take on over and add your comments. One thing I got though is he said, and I don't remember if it was in this particular slide or the next one, this to me looks like Unity, I believe they're called, or Unitary. He talks about matrices where you typically have zeros and then the values you care about are on the diagonals. But one thing, and I don't remember exactly, he talks about that symbol, yeah, word denotes the adjoint, taking the transpose and complex conjugate of a potentially complex matrix. Transpose a lot of times means you've altered it in some way, like a reverse. And he talks about this here too, where, let's see. So he talks about, okay, so we have this set of, our goal is encoding matrices as QPU operations. That might sound simple. If deep down they're described by matrices, then just find the one, hey, that's easy, that has the same matrix as the data to be encoded. Unfortunately, only a subset of matrices correspond to actual valid QPU operations. So once again, we realize all the matrices you can design under the sun, not all of them can be represented operations. But this was the interesting part here. He said in particular, valid QPU operations are described by unitary matrices. And so this is again, scratching on the brain cells in the back of my head of what that meant. Unitary matrices are where you can have almost an opposite, and that's not the correct mathematical term, but if you multiply them together, you get one. And this goes right back to, well, why is that important? Well, if we have a unitary matrix, that means it's got an opposite. And sure enough, that goes back to, it ensures that our circuits using them will be reversible. And remember, we had that requirement way back in chapter 5. So this is again starting to piece things together for me. Oh, I can do these operations to represent this matrix. Oh, wait, you can't do all matrices. You can only do these special ones. But the special ones you're doing happen to be reversible. And that's where we come and we're kind of carving out our subset of matrices that we can use. And so that kind of makes sense to me. I wouldn't want to try and code a matrix that was invalid. One, I couldn't. But B, here's the reason why. Because it inherently wouldn't be reversible. So again, I feel like this is a chapter or the whole book that on my third or fourth reading would start to make a little more sense. But he says the good news is that given the Hermitian matrix H, it's possible to construct the associated other matrices. And then this goes back to, oh, well, again, those unitary matrices tend to have this sort of style where you've got a lot of zeros and the information's on the diagonal. So, okay, even if I don't quite understand what this means, it's leading me back to my understanding of if a matrix is reversible, it would fall into this pattern. This pattern of matrices are these Hermitian matrices. I've never heard of those before, but I gather all together that's a class of matrices that we are able to use for our operations. So something I'm interested in learning more of later. He talks about why it's called quantum simulation. And he talks about it because we're simulating behavior. So molecular material simulations, he also talks about it's often used in physics or chemistry. He talks about down here. And we're getting towards the end here. So he says, okay, well, this is really hard. It can be. Our requirements are, I think I may have skipped a thing here. And a couple of requirements. Well, one is it has to follow this format. Again, this is where I start getting a little lost. He talks about, well, we need to make, he has this form where he uses a matrix, he's using T for some amount of time that he's using it. Again, I don't know if that's a chemistry thing or something else. So he talks about, okay, again, we have this complex thing that's hard to do, and we're going to break it down into a set of steps. So basically, he says there's a way that if we have these complex matrices that we're trying to break down to operations, there's really these 3 steps. The first one, you deconstruct it. You find a way to split that set of operations into a sum of simpler operations where done consecutively, they actually do what the large operation is supposed to do. And we see that in math and programming and stuff all the time. So that seems to make sense. Then we find efficient circuits to use that to build out those operations, and then we put them back together. And so he goes into the math of why this works. And he says, let's talk about reconstruction first. And so if we have our main operation or our complex operation is actually built of these little ones, then again, we get back into these exponential functions. And again, I kind of got lost here, but just looking at the diagrams, I thought, well, I'm assuming this works. This makes perfect sense. So we're going to deconstruct a complex problem into this a series of small problems. The small problems are easy to tackle. We've got operations like those basic ones we learned back in the previous chapters. And then again, at the end, taken in series, they do the large complication problem that we've been trying to do. And then he talks about the cost of it. And this was interesting because we haven't really talked about performance a whole lot. And so he describes it not in the cost of time as far as like seconds or milliseconds or anything like that, because that's hard to do, especially with computers being, they're coming out with breakthroughs all the time. But he talks about it in the number of operations needed, because again, I think that's the fundamental limitation we have right now, how many qubits we have, how many operations we can perform. I didn't remember where he said it. It was in a particular page, but he said one requirement was trying to make sure the circuit was efficient. And I thought that was interesting because again, we haven't really talked about efficiency a whole lot in this book. And I kind of take it for granted, well, quantum computers are these Marvel superpowers. So is efficiency really the same thing as what we consider? And I'm sure it is. And we just haven't touched on it a whole lot. And that's the end of this chapter. Any comments from you two?
Well, when it comes to efficiency, again, kind of seeing how like the IBM environment works, and you typically run something 1,024 times is kind of the default value for the number of times you want to run your circuit. So just the fact that you're running something that many times, it seems like you want it to be as efficient as possible.
Yeah, I see this as just a preview of what's coming. So it's kind of to whet our appetite of, because the upcoming chapters are more about applications and start to get more practical. So you got kind of the abstract one. So thank you for jumping in and taking the very abstract topics. You did a fantastic job. Thank you. So we're about at time. So this is chapter 9, right? Is there anything else that you wanted to share on this matter, or is that pretty much covered? Okay.
Then we're right on to chapter 10. Great.
Okay, so we've got quantum search. So, we want to trade off. So I don't know, Jeremy, if you want to take it or I can.
Yeah, I'll take it.
You'll take it? Okay. So I'll go ahead and stop the recording and we'll be back with 10 next week.